A flashlight beam strikes a pane of glass, n equals 1.5, at a 60-degree angle to the normal. What is the angle of refraction? All right, on a problem like this, drawing it helps sometimes, so let me go ahead and do that for you. Okay, so here I drew the problem for you, where you've got the light is coming from the air, and then it's going through the glass, and it's refracting at this barrier. So
through the looking glass, people.
Exactly. So you end up with actually a smaller angle here than you started with, and to kind of help you with that, you can sort of picture if you have like a race car that's going here, it's going faster on this section. You can think of it like this is asphalt and this is sand. So if you picture a race car that's moving in this direction, the wheel on the right side is going to hit the sand and start going slower. But the wheel on the left side will continue going, and you'll get a small rotation in the car. And that's exactly what the light does here. It bends so that the angle is less intense. By the way, the index of refraction for air is n equals 1, and the index of refraction for glass is 1.5 according to the problem. So now it's just a matter of running Snell's law to work it out. So let me show you that. Alright, so to solve for theta 2, we use Snell's law, which is very easy to remember and even more fun to say. Snell. Professor Snell from Harry Potter, whatever. So it's just n1 sine theta 1 equals n2 sine theta 2. In other words, how fast the light travels through both of the mediums, determines what the angle is at each one. So if it goes from fast to slow, the angle shrinks, and vice versa. It actually turns out if you started with the flashlight here, you'd get the exact opposite effect. But anyway, it's just a matter of throwing those numbers in to figure out exactly what the angle is going to be, so let me show you. Alright, so with a little bit of work, you should get sine of theta 2 equals 0.59. But the problem is, how do you solve for theta when it's buried in this sine function? Well, all you got to do is you just go in your calculator and you type this in to get the theta by itself. You go sine minus 1 of 0.59. And if you punch that in your calculator, you should get theta 2 is equal to about 36 degrees, something close to there, which kind of agrees with our drawing. This angle is smaller than that one. And by the way, that's 36 degrees from the normal. I drew this line, the line perpendicular to the barrier, because that's the angles we care about. Don't use these angles. Instead, use the angle from the normal. That's the one that is what Snell's law is talking about. See you on the next one. Next problem. The critical angle for a certain liquid air surface is 44.7 degrees. What is the index of refraction for the liquid? Hint, think about what takes place just before, just a fraction of a degree before the critical angle occurs. So let me just give you a really quick recap of what a critical angle is all about. Alright, so I have a little bit of a drawing for you to kind of talk about this whole critical angle stuff that this problem is talking about. What I mean by the critical angle is if you have a light that's going from something slow to fast, so maybe this is like water and this is air or something like that, the index of refraction here is bigger than the index of refraction there. You have a bigger value of n, so you have a big N here and a small n there. And when you have that happen, then what happens is the angle from the normal actually increases. So if you look at this thing, this angle is smaller than that angle. It got bigger. And as it gets more and more extreme, you get like a super angle over here. Well, the goofy thing is, this angle cannot grow beyond 90 degrees. There's no such thing as theta 2 being like 91 degrees, because it wouldn't be going through the material anymore. It would be staying here. So what happens is, when this angle gets too intense, when theta 2 is 89.999 degrees or whatever, when theta 2 is as big as it can possibly get, then if you make this angle here any bigger than that critical angle, then you're going to get total reflection. And we did that in class with the laser that was underwater, where the laser light could no longer escape the water anymore. And that's why when you're far away from a pond, you can't see fish anymore. You have to be close to them so the angle isn't too steep. So now that you know what a critical angle is, I'm going to make it as simple as I can. If you see the word critical angle in a problem, just set theta 2 equal to 90 degrees and see what theta 1 is. I'm going to do that for you. And pause the tape and take a look.